Okay, so I'm going to attempt to start in here. There ought to be a written outline here, but I don't know how to say what the outline is very well, so it's just going to become apparent at the end. But I'll just try to tell you into the air what the sort of direction is that I'm going to try to go in. There are sort of three. Is this right? There are three matters that I want to go over, but maybe there are only two. One of them is starting with some basically clarifications that I need to make about Hilbert transforms and stuff moving around in circles, and going from there into going back to the block one pair of delay line thing, and showing you what happens when you try to make oscillators be coupled together. So there's the whole coupled oscillator thing. So the coupled oscillator thing has this preamble, which is not about coupled oscillators, but it's just sort of stuff about the Hilbert transform that might just, well, that is missing and anyway might clarify things. And then after that, there's the question about feedback systems that involve actual delay lines. So far, all the feedbacky stuff that's been going on, as far as I can remember, has all been with a one sample delay. There are, of course, interesting other kinds of situations where the feedback has real delay, like it would in a room, say. And then there's the situation where the feedback doesn't have any delay at all. In other words, you try to make things happen in continuous time. So it is, in fact, three topics. One topic is coupled oscillators and the like. Another topic is delay lines and how they act in feedback systems. And another topic is things that you do that are or modeling things that are happening in continuous time. And that's kind of it for theoretical topics. And then there's another thing that I want to talk about, which is actual real feedback situations where reality is part of the feedback. And the examples that I know of about that have to do with that are basically the repertory of both audio and visual pieces that involve feedback in some way. So I'm thinking of a couple of pieces that got mentioned this morning: Wolfman and Pendulum, and that I am sitting in a room, and then another kind of related one, which is by Nicholas Collins, and also the idea of using video feedback, which people have made all kinds of wonderful pictures with. And video feedback works quite differently from audio feedback because it can be spatial as well. Well, it can be spatial in a totally different way. You can put stuff places, which you can't do in space and in audio, so or at least not in the same way. So that's another thing which sort of is kind of the capstone or the last topic. So we have 3 sessions left in which to take care of these 3 serious topics, and then this one even much more serious topic, which is how these things actually have made it into the repertory. Which, in fact, I should say, isn't going to be heavily technical, because things that have actually made it into the repertory usually are based on much simpler kinds of things than all of these high-fluting techniques that I'm trying to show you. All right. So, all right. So the one matter, which is just by way of clarification, or perhaps just being a little bit more complete than it was before, is just going back and talking about quadrature and feedback, or quadrature and distortion, I should say, without even feedback. And my reason for talking about quadrature is that all of the feedbacky stuff that I've been doing has gotten a lot easier when you deal with things in quadrature, which is to say as a sine and a cosine, so that things race around in a circle instead of going through 0 in 2 different directions. So this is kind of about quadrature, but it's not really about feedback. It's just about something simpler. And what I should do is just start with nothing as usual. Oh, that was interesting. Start with nothing as usual. And let's see, I'm going to say new and make myself have a reasonable font. That's more than reasonable. And then start doing things. Okay, so the back to square one here. Let's distort an oscillator. So what? Hey, oh, not this again. All right, now what do I do to fix this? I deal with the fact that my did that fix it? That fixed it, okay. All right. This is my volume control that sends X Windows events at many times a second, which I think I have stopped now. All right, so what we're going to do is make an oscillator with a controllable frequency, like this. And then we're going to, first off, listen to it. Oh yeah, and of course, find out whether we have audio. Let's give it a real frequency, give it some amplitude. Hey, all right, that's a little bit too good to be true because I didn't actually check audio today. All right, now what we're going to do is distort it. Oh no, I'm not going to do that. Distort it by clipping, and to clip it, say, you can just say clip minus a tenth and a tenth. And of course, I was showing you all these soft clipping functions like cubics and so on, and okay, all this stuff applies in exactly the same way. But anyway, doing it just brutally, all right, something close to a square wave, right? Now, here's the thing I want to mention about this. Let's put this thing through a Hilbert transform and start doing things in quadrature. All right, so output. Once more, the real part sounds like a thing. The imaginary part, if I may call them that, but really it's just another sinusoid at 90 degrees away from the first one. Sounds like that. And of course, I could clip either of these things, and then you would hear the clipped sinusoid, and happy. All right. So now we go grab our friend unit polar, which I forgot to copy into this directory. So what are we going to be called? One unit? I don't know. Hilbert Distortion. All right, and now I got to go do some bookkeeping again. All right, so now I have a copy of unit polar. And, oh, polar. I think there was a tilde in the name, yeah. Okay, so the deal here was you could put something in here, and, well, you could put real and imaginary part of something in here, and it does all sorts of nonsense that that has been cooked up in order to give you just the, what's the right word, just the amplitude of that thing, which should just be 1. I'll check that. Oh yeah, let's get graphic. So we'll say array, scope, I don't know, let's see, 500, tab right, tilde scope. Sorry, this is boring. And here's, no surprise, amplitude is 1, and what is the, so that now is the, all right, so there's a thing running around the unit circle, so of course the radius is 1 all the time. And then what's going to be the phase? Well, it's just going to be a nice sawtooth wave. Right. And now you can go down the rabbit hole of, oh, now that we have a phase and an amplitude, we can plug this into any C-sound or PD instrument that we want that is oscillator based, and then we can have this sinusoid drive our favorite oscillator. And then of course you take a microphone to something and have that drive your oscillator, and then you can have fun all day. Right. So that's, and that's the thing that I was showing you with the guitar patch maybe on the second day. All right, now, all right, so let's, first off, how do you get the sinusoid back? You just, sorry, no, cancel. How do you get the sinusoid back? You just take the cosine, sorry, dyslexia is setting in. Take the cosine of the phase, which, by the way, is in perfect units because cosine likes its phase to be from 0 to 1. And then we'll multiply by the amplitude. And this is going to be such a good reconstruction of the original signal. Let's try it out. It should sound like a sinusoid, right? And it's going to be such a good reconstruction that we could even compare it to the original. Well, the original. We could compare it now to the output of Hilbert, like this, and verify that there really is nothing left except some truncation error. All right? So somebody ask a question because I've already...
That's truncation error. It seems pretty significant.
It's pretty significant, but the thing about tab right tilde is that if it goes negative, it will be negative. There's something about the float to fixed conversion when you, oh no, it's not the, I'm sorry, it's not tab right, it's scope's fault. Scope, if the thing is positive 10 to the minus 19, it's up here, and if it's negative 10 to the minus 19, it's down there. So if I wanted to make that go away, I would add a 1,000th to it, say, just to make it not fall right between 2 pixels. And, well, I don't know, got better. Didn't quite get perfect. So actually, yeah, it looks like the ripple is actually on the order of 1,000th, which is kind of not so good, but that's because unit polar isn't really taking the arctangent, it's messing around. It's doing a polynomial approximation to try to be fast, which is stupid because, well, it's not stupid. I needed it to be fast in the application that I had when I made it, so now it's this fast but not perfectly accurate version. All right, so my purpose in doing this is this. Of course, now if we took this and clipped it, so let's get rid of this, oh, don't know about that. Okay, so here's the sound. Okay, now we're going to clip it, just like we did before. Okay, but now we're going to do this. Rather than clip it there, let's clip this one. In other words, we're just clipping the radius output, but we're not doing anything to the phase. Any predictions of what you're going to hear? Do what? Very quiet. Well, point 1 is minus 20 dB, so it'll be 20 dB quieter than the original. And furthermore, the timbre is perfect sinusoid, because all we did was instead of putting 1 times this cosine, we're now taking 0.1 times the cosine. And so what we've got is now a nice thing that will clip our oscillator, but will never distort it. So now I can just do nonsense like this. Okay, so let's just make a nice computer music instrument. This one?
Yeah, is it kind of a DC level? Or?
Yeah. So it's this.
Okay.
Oops, no. Oh, I disconnected the oscillator.
Right, so clipping
it's
DC, of course, would have
there.
distortion.
Yeah, so clipping it then replaces it with same thing but smaller, right? That's not 0, that's 1/10. All right. So now we got our nice computer music instrument. I'm by the way deliberately using a lousy envelope. And of course, if I don't want it to click, I should fix the thing so that it has a beginning phase of minus 0.25. Let's see. Should I explain this? I should explain this. If you want this thing not to click, hey, go away. Here's an instrument that'll click. Except it won't do anything until I turn it up. Click. Well, sometimes it clicks, depending on phase. Just fix the phase so the thing is 0 right when it jumps to 1, and then it will. As long as you wait for it to be gone, it won't click anymore. And if you want then to have it work even okay if it's already playing when you do it, then you need to take a snapshot of the value that it's at and hold that value and add that to the new thing that you add on top of it. Okay, so this is a beautiful computer music instrument. And now we're going to clip it. Oops, sorry. In the same way as we've been doing. And then, of course, the amplitude change will, or modulation, or whatever you call it, envelope will turn into a timbral envelope, and we'll get this. Right? But now, if we do it the other way by clipping only this amplitude, then we get this. Everyone follow this? All right, I'm pulling a fast one. because this only works this dramatically when you feed it a pure sinusoid. If I gave it anything more than just a pure sinusoid, this wouldn't be so cool. But what is happening when it's a sinusoid is this thing is erasing the phase from it and then clipping the amplitude that is not the amplitude that has the phase, but just amplitude. And therefore, all you get is this envelope, which was ramping from 1 down to 0, ramps from 0.1 over to 0.1 over 9/10 of the note, and then down to 0 over the last tenth. Right? So you get beautiful sustain, just like on an electric guitar overdriving an amplifier, and no distortion, unlike an electric guitar overdriving an amplifier. Has everyone see what I'm up to here? Okay, now, just to be honest, I should now go back and show you what happens when you do this to something that is a little bit more than an oscillator. So let's take our nice oscillator, and what should we do? Let's have there be 2 of them, and let's have them be at an interval. Oh, this is cool because we can make the interval anything we want. How about a perfect fifth? And by the way, those of you who have perfect pitch will thank me if I change this like that. All right, so where are we? Now we have before and after. Before is this. Sorry, forgot a couple things. Try again. Okay, everyone knows why that happens. And now we do it to this network, and all we get is basically just a little bit more smoothness. So I'll mute this. So what we did was we changed this kind of clipping. That's just hard clipping the sum of 2 sinusoids to a small value, right? And then we were able to change that to the much more mellifluous sound that is this one. Well, mellifluous, I don't know. Anyway, it sounds a lot more band limited anyway. I got rid of all the crunch, right? Of course, the other way to get rid of all the crunch, or to try to attack the crunch, is to make the clipping be soft clipping instead of hard clipping. And I claim, although this will depend on what kind of signal you throw into it, that those 2 things are, in fact, things that you can apply both of to get all the more better happiness. In other words, if you don't like the sound of hard clipping, there are 2 ways you could avoid doing it. One is don't hard clip, just use cubic function, arctan, what your favorite clipping function. And the other thing is to do this, and the even better thing, depending on the signal you put in, might be to be doing both of them. Both this phase trick and the arctan business. All right. So this is, now, it'd be nice if I made this in a way that you could use it. So what I'm going to do is I'm just going to save this patch, Hilbert Distortion. So this is just about distortion. Now, the other thing that I should be telling you about that is related to distortion is, of course, people's attempts to make good compressors. And here I have to give a virtual doff of the hat to Katja Vetter, who was the first person to point out something that should have been obvious to everyone, but basically was only obvious to her until she told everyone else, which is that you can apply the same kind of thinking to envelope following ordinary signals and use it for whatever you use an envelope follower for, in particular compression, which is, of course, the thing that no one can do terribly well, but which everyone thinks the old box that was made in Britain in the 1950s that has tubes in it sounds better than anyone's computer algorithm. So compression using Hilbert transform looks something like this. So what I'll do is I'll just I won't actually go to all the hassle of making a compressor again because everyone knows how to do that, but I'll make envelope followers, and you can see how the envelope follower using the Hilbert transform just way outperforms the envelope follower that doesn't, at least to look at. And in fact, when you do all the work and actually make a compressor out of it, then you'll A/B them, and then you'll decide that one of them sounds good for one thing and one of them sounds good for another, and then people will have arguments for years. So we'll just live in that world, but that's okay. So I'm going to do save as and go make a second patch, which is envelope following.
stay on the school server indefinitely?
Unless I get so embarrassed I have to take them down. I think, yeah, I'll probably just leave them forever and just not tell people about them. Because I suspect it might be a good thing to be able to look back on later. Yeah. Not least for me. Okay, all right, so envelope follower. Okay, so here, as before, the thing to do, or a thing to do anyway, is to start with one oscillator and show how the thing works perfectly, and then to show you reality with a couple of oscillators and show you how it doesn't really work quite perfectly, but it still does pretty okay. It still seems like a step forward. All right, so here we go. Get rid of the oscillator, and now we're back to tone, good. And now what I'm going to do is just try to do an envelope follower and let me do the naive way first, so that then you can admire the sophisticated way and how much better it is. So to do that, rather than do this clipping thing, I'm going to take the signal and square it and then low pass it. That's all I really have to do for this context. Envelope followers come in many, many flavors, and probably I ought to be telling you more about how you could do better, how you might be able to do things other than square it and get happier in other kinds of situations. Like take the absolute value instead of the square, and then you get a different kind of envelope follower. It goes on and on and on. And no one will ever see the end of it. All right, so now I'm going to first off, let's make this graph a little bit longer. Let's make it have lots of pixels in the horizontal. And I'm not sure how many points to give it, so I'll just hold it there for now. Oh. And the other thing is I only care to look at values that go down to 0, so I'll do this. I'll give it a -100th, and then I don't need all those pixels. Oh, that's a horrible idea. I don't even know what that'll do. All right. Okay, good. All right, now I have a scope and it's sitting at 0, and I did something a little sloppy to make you be able to see 0. All right, and now I'm going to make there be 2 of them because I'm going to want to AB 2 envelope followers. No, not yet. No, first off, I'll just show you what happens here. So now what we got is, we've got a button here that turns our oscillator on, and then we have, we're going to square it. I don't need the clip anymore, but what we need now, is a, can't hear it until I give you one of these. So this is what we're going to listen to. And then we're going to low pass filter it, and I'm just going to go for the cheapest low pass. And then we will write it into the scope like that, and then make the button start the graph. Look at that. That's what envelope follower looks like. Well, okay. How could we get this thing smoother? Or at least better? Well, one thing is we could just try envelope following something with a higher frequency. And then the filter will have a better job, or have a better time filtering it, and then we'll get less wiggle. But of course, you can't tell the guitarist just to go up 3 octaves so your envelope follower will work better. So in fact, yeah, let's go back to there. And let's just say, well, let's make the low pass be a lot lower. And then, well, okay, but, all right, properties. Let's see, this is not very much time. This is 500 samples, so what is a good amount of time to look at? 1/10 of a second, so 4410. And now we have kind of a disreputable, but okay, envelope follower. Now, and now, of course, when you take this and use it to do, for instance, a compressor limiter or something like that, you'll divide by this, and this wiggling will give you harmonic distortion, and then you'll do all the things that you can do about that. Okay. Of course, you could just do this. You could just use this radius here. Now I need another tab right. So I'm going to call this one scope 2, and I'm going to duplicate this. And call this scope 2. let's see what we got. So I'm gonna I gotta give it a signal like this, right? And maybe I've forgotten something else, maybe not. Look at that. Yeah, I should have told you about the factor of 2. This is because the RMS of a sinusoid is only, well, the mean square of a sinusoid is only 1/2 of the peak, and the RMS is only 1 over the square root of 2 of the peak, and so this is the square root of 2 quieter than this is. But that's a factor, you figure out what it is, and then you correct for it. It's no big deal. But notice how much spiffier my envelope follower is. Except for one teeny little thing that isn't going to really bother us yet, but will start to egg us a little bit later, which is look at that attack down there. The attack doesn't just take off like an honest one-pole low-pass filter. Instead, it reflects the fact that there are all-pass filters in this Hilbert transform that had to wake up, and they have a little bit of a wake-up time, which is what you're looking at there. And I don't know, I could show you what that, well, would that be worth it? I could show you what actually comes out of Hilbert. That might be worth it, actually. Okay, so let's, sorry, this is either a digression or it's not, depending on your point of view. I'm going to just hook these things up into the tab right so that you can see what Hilbert does when I feed it that sinusoid. Yeah. I got to do a couple things to make this work. Got to drop the number of points. Is this worth it? This is actually really, oh gosh. It's not really worth it, but it would be worth it if I made myself a third one of these things. Actually, yeah, and fix this so that it was going to do the right thing.
Hilbert is an internal object, right? It's not a beat, it's not a patch.
Hilbert is in extra. I'm going to make it 100th of a second. Yeah, there it is. Okay, now you're looking at what Hilbert actually does to the sinusoid right during the attack. It takes it a cycle to decide what it's going to do, after which it has calmed down well enough that you can then, you see it's gotten itself worked out here. But it took Mr. Hilbert a cycle to get itself really giving you this thing in phase quadrature. You look mystified.
Of course, waiting for the part where you explain why it takes all pass filters time to wake up and what that means exactly.
Actually, I was using sloppy language because I don't know what the correct, crisp, honest way of saying that is.
There's some kind of tracking error, it seems, or so what's that coming about?
Well, this is stupid, but think of it as some complicated mass on a spring system where there are, I believe in this case it's a 4-pole filter, so there are 2 masses, and the thing's just got to get shaking right, and it just takes it a cycle to get into its swing. But beyond that, I actually don't know the details about how to talk about what its relaxation time is, except just to try it and look at it. And by the way, I have no idea whether the complex part behaves better or worse than the real part, sorry, the imaginary part, but that's an easy thing to find out because, how did this work? Sorry, I have no idea why this is working at all now, but anyway, it's working, so let's just enjoy it. Do this. I see. What I did was I copied the table. I'm not actually, all right, what I really need to do is give it a new name, and then really start writing into it. Oh, mistake. All right, scope 3. All right, so we're still looking at the real and imaginary. No, we're not going to look at those anymore. We're going to look at the 2 envelope followers. The stupid one on top and the cool one on the bottom. This is because eventually we'll feed it mixtures of sinusoids and check it out there. Okay, and scope 3 is just going to be watching the Hilbert transform have trouble get off the ground. So now I'm going to look at the real part of that. Okay, no surprise, it didn't change because it's the same thing I measured before. And now the imaginary part. Same basic deal. Eventually it settles in, but again, it takes a cycle for it to do it. The cycle's not a terribly long time at this kind of frequency. But if you want to torture a Hilbert transform, you give it a very low frequency. Because, of course, if you give it DC, here's your real part, what's your imaginary part? It could be anything. So the thing isn't actually even defined. Well, it's not quite the right thing. But what you should do to phase shift a DC signal is not well defined. So this thing will just start having trouble when we give it a bad low frequency like this. Yeah, no, it's, you know, it just can't perform anymore. All right. I believe by the time you get up to 30 hertz, you're doing fine. Oh, no, not even. But even in 30 hertz, you're having trouble. But up here at reasonable frequencies, then suddenly the thing is doing a great job. Okay, so. All right, so now it's time to feed it the fateful mixtures of sinusoids. I don't know if I need to give it this or not. And now this is the acid test, because these are equal loudness in a sort of a reasonable situation. You'd expect there to be a little bit more of an uneven mixture of sinusoids, but let's give it a try. And now we've got. All right, so we still have the factor of square root of 2 difference, and the truth is oh wait, are we filtering the same? We're lop 10 there and lop 10 there, yeah. So we're actually comparing apples and apples. So basically the situation was, it got rid of the high frequency wiggles for us, but it didn't give us something that looks actually more accurate necessarily. And once more, if we now, yeah. And now if we say, well, this isn't fast enough for us anyway, I want this thing to go at, say, 20 hertz-ish, then you'll have a more realistic kind of a thing. Yeah, and basically still it's like, can't do it, but it at least does, it at least doesn't give you the high frequency products that the other one did. So this is perhaps a better way of doing envelope following for doing compression or other kinds of things. But the betterness is at its extreme when you have a pure sinusoid, and gradual and is somewhat attenuated when you give it real signals. Still better than nothing. I mean, it's a better thing to do it than not to do it if you're trying to make a compressor. And again, there's this little. It doesn't even seem to matter in this grand scheme of things, but there is this moment when the thing is actually trying to get itself off the ground. Okay. And I believe it is now the case that if I push the frequency up, so it's 220 now. If I go up an octave, yeah, the thing gets better, but it doesn't get proportionally better. It just gets to where the low pass filters are more effective at getting the fritz out. Okay, so that is using Hilbert transforms to improve envelope following for compressors or other purposes. And that again is Katja Vetter speaking, and not me. Or actually, it's me copying what Katja Vetter has come up with. On her webpage, you will actually find that she has her preferred form of the Hilbert transform. She is using a filter that is, she's using a lower order filter than Hilbert, so that the thing will kick off a little faster and be gentler to her transients at some expense to phase correctness, which one can get away with in a situation like this. All right. Now, so that's basically so much for that. Now what I'm going to do is go back into doing these block 1 filter things, and what I want to do is jump back to the example which was about the oscillator feeding into the filter that had the automatic gain control in it. Okay, so let me go get that patch for you and review it a little bit, and then start messing with it. Yeah, I think I do. Yeah. Sorry. Okay. So we go back, and it was, I'm pretty sure it was it more resonant? All right, this will do us even if it wasn't the right thing. Okay, so this is where we were most recently, and I'm going to save this under this maybe the same name exactly. 3 more resonant. Okay. So what we were at when this was sort of a coda, because this is a thing that I sort of sloppily visited twice on 2 different occasions, and this is the second occasion I came back and said, oh, and yeah, by the way, you can mess with the phase. So I'll just quickly remind you what we're doing here and then move on and do something that's more useful. Or not more useful, but more different. So what was happening here is the following thing. We've got an oscillator testing a filter out, and the filter is this thing with a small block size. It's block tilde 1, and it has a real and imaginary part called TED. And what's going on here is that it's taking the real and imaginary part and first off at a low order of sorry. Let me do this before I try to explain it, and then I can try to explain it. So why do we not have unit polar here? Huh. All right, we're in... Oh, I've saved it in the wrong directory. Ugh, sorry. We are not in the right place. Oh, we are. We're in 6. Why is small blocks... Sorry, I am not understanding why this believes it's in this directory after I just saved it in the other directory. Let's close it and reopen it. 5. We want to be in 6. 6, and we have unit polar. Okay, now. All right. I don't know why they haven't. Okay. I'm going to leave unit polar around because we're going to want it later, but I don't want it right now. And what I'm going to do is get rid of all this wonderful stuff that we were doing, which was messing with the phase, and instead just mess with the phase in a constant way, which I can do like this. Just gonna, we'll add something to this later, but right now we can just do that kind of thing. And there's the radius. We are controlling the radius by, okay, and this is a thing I have to say. So, we measure the radius, we subtract 1, and then and that gives us how the radius is different from radius 1, right? And then what we want to do is correct the amplitude by perhaps, by multiplying by 1. So here we're multiplying by 1, except maybe multiplying by a little bit more than 1 proportionally as how we weren't where we wanted to be. And this proportion now is a speed at which we reach the radius that we're desiring. Right? I didn't explain that terribly well at all. So suppose the radius is 2 here. Then it's 1 too big, so we subtract 1 to find it's 1 too big. So how much are we going to correct it by? We're going to correct it by 1% of that difference per sample, this is, right? So we're going to multiply it by minus 0.01 so that it'll become, correct this by minus 1/100th. Add that to what it should normally be, which is just 1, because if we just feed it 1, then it will just maintain itself. And then don't allow it to do anything crazy like blow up or kill the thing by zeroing it out. So this creates a gain which is usually around 1, but which will vary slightly from 1 to try to correct the amplitude. And this thing should, at least once we have given it a little bit of signal to enjoy, it should start oscillating. And I need to give it a very nice low number here. And let's see if it's doing anything. Yeah. So now we have a nice oscillator. With terrible units. Let's fix the units. Hey. That was interesting. Don't know why we didn't hear that. 1,000 even. All right, good. Okay. All right, oscillator. And now part of the joke was that we don't need this. This twist is not doing anything. Part of the joke was now we can put an oscillator in here and make it hate itself. So we feed it just a little bit of this nice oscillator. Wait, that's too similar a frequency. Okay. And now I start pumping it with this oscillator. And it wants to oscillate at its frequency, but I'm giving it a different frequency to oscillate at. And so then eventually I force it to oscillate at my frequency. then I just get torturing a nonlinear filter, right? And now the cool thing is there's a regime in here where it can't decide what it's doing, and then it makes various kinds of multiphonics. It's not interesting. I'm not sure how I make it be interesting. There, now I'm making a fight between two notes that are at an interval, and now we're just getting a multiphonic of those two intervals, right? I should, at this point, I should say, if for further investigation, this is probably related to how real multiphonics are made on instruments, like reed instruments. But I don't think anyone has systematically figured that out. I know people have studied it, but I don't think anyone's really got the last word on actually what makes multiphonics come out of clarinets and saxophones. It's something like this, which is to say the resonator is interacting in some kind of nonlinear way with the reed, and you have to pretend this is the reed and that's the resonator. But there is stuff going on there that we can't deal with here, which is that the resonator is actually going back and telling the reed what to do, and they're having a fight about what frequency to operate at, which creates the multiphonics somehow. And that's as much as I'm going to say about that, because that is Tamara Smith's expertise, and if you really want to know about that, ask Tamara and don't ask me. All right. Okay, so this is nonlinear filtering and making a multiphonic, and this is essentially review until we start messing with it, which is what we do next. Now, the messing with it that I want to do next is to respond to that criticism I made about how this isn't like a wind multiphonic, which is to say that the filter can react to this oscillator, but the oscillator is not reacting to the filter. So the next sort of logical thing that you might want to do is make the filter, in fact, be two oscillators that can therefore reciprocally mess with each other. And then you will have basically a much larger palette of possible ways that you can make the two oscillators interact. Right? So that's the next step. And to do that, the thing to do is go in here and make this thing have twice as much junk in it. Now, before I start adding junk, I should do a thing which will just help us a little bit later, which is introduce, if I put it there should be somebody named Twist. No, because where did I put it? Oh, let's make it. All right, what I'm going to do is I'm going to make an abstraction that just contains all this good stuff here for multiplying by for multiplying by a unit complex number, or to put it another way, for rotating a point in two-dimensional space. So I'm going to say copy, new, paste. Oh, it got bigger. Don't know what's going on with font size now, but let's just pretend nothing interesting is happening here. And we're going to call this a nice signal inlet. Ooh, inlet, please. And then we're going to have two inlets, which are going to be the real and imaginary part, and then two outlets for the product. So real times imaginary. Sorry, real times real, real times imaginary, imaginary times imaginary, imaginary times real. That, and then outlet twice. All right. Now, if I did that, okay, then we're going to call this twist. I'm just going to put it here for now. And now, theoretically, if I recreate it, there it is, twist. Okay, so the deal is you put in two numbers which are complex, two inputs which are a complex number. Outcome's a complex number. It's a little bit ugly because I wish they were spaced the same way, but that's just a limitation. And now I can get rid of all this junk. Oh, I think I want that. I'm going to throw this, I'm going to make a signal out of this. This is a bug in PD. Inlets do not know how to promote float to, inlets of subpatches don't know how to promote numbers to signals, so make a signal out of it. And now we're salting it with a little bit of noise so that it won't just be 0 forever, which is what it would do if we didn't do anything. And now we don't even need a signal inlet. So let's just not have one. Oh, actually, you know what? We may need it later. It might be fun to have it later, so let's keep it. Because we could go back to making this thing a resonator later on. All right, and now what's going on is we have a number here which is, let's do this. Okay, we have a number which is now the angular rotation that we're going to have, and we have this stuff which is stabilizing the radius at 1. And now let's check and see if this is actually still making sound as we wish. Let's see. Sorry, I'm also trying to figure out how to make the thing work out spatially because we're about to throw a bunch of more junk in here. Okay, now I'm going to look at the parent patch. Yes, okay, so we still have our oscillator going. Whoa, sorry. What did I just do? Well, this is interesting. Okay, first off, I forgot to get rid of this test signal, which is what we're listening to through this patch. The second thing is, oh, that's all right. That I'm not worried about. But why is it refusing to make a sound? Oh, well, all right. We have to just do the usual thing. I don't know which one I'm going to use. Just look at some values and see why it hates me. Oh, that's interesting. Let's give us some nice width. Little tiny values, those are negative exponents, so it hasn't gotten itself off the ground. Perhaps, and then what that should mean is that it should now be multiplying by slightly more than 1 here. Which it is. It agrees that it's too small and it's trying to correct, so this is the correction it makes when it's too small. So what that means is that I have hooked up my complex multiplier wrong. That's a horrible thing to find out. Real times real, imaginary times imaginary, subtract. Real times real? No, thank you. Real times imaginary. Imaginary times real. Add. Sorry. All right, we're back. Except it's now too loud. Arr! All right, shut up while I find the volume. Here we go. All right. Okay. So this is the same kind of oscillators we've been messing with before. Let's just for sanity's sake, let's keep this around. I still hate the range here. Okay. Actually, what I really should do is I really should make this be a frequency in hertz so that we can know what we're really doing. So the frequency, so to convert frequency to hertz, what we need to put in here is how many radians the thing has to rotate. No, how many cycles, sorry, the thing has to rotate by per sample. So that just means we divide this thing by the number of samples per second. In other words, we need cycles per sample, and we've got cycles per second. We just divide by the sample rate. So here, I believe. No. Oh, that might be. Is that A? Cool. All right. So we actually believe we're specifying the frequency now. All right. Be quiet. Questions about what I've done so far? Sorry about the messiness. No, everyone's with me. Okay. Well.
I'm not certain what we're doing in that third inlet.
Okay, so let's go in there. So the third inlet is an angle, or it's an angle in cycles. And so we're taking the cosine and sine of it, and that's creating a complex number which encodes the frequency that we're asking for by saying by what angle we're going to rotate by each sample. So this is, maybe I should have said something about this. here's the thing about complex numbers. Things always get very error prone when I start doing this. All right. Oh boy. I don't know why this is so hard. There we go. Okay. So deal about complex numbers is if I have one complex number here, I'm going to call this, I don't know why I'm using capitals, and then some other complex number, which is my sample at time n. Then if I made a thing which is z times x n, that just serves to rotate x of n by whatever angle z is at. So, and this is the fact about complex multiplication, that the angle of the product of two things is the sum of the two angles. And that is being encoded here because this is the number z, and what's coming in here for, at each moment in time n, that's x of n. And then this is x of n plus 1 coming out. Or zxn. Right. So that's why this thing oscillates, in fact. And that's a good thing to know because, oh, yeah, and the other thing is, of course, that is an operation which preserves the length of this point from the origin. In other words, even if I gave it something, going back to the picture, even if I gave it something that wasn't a unit complex number, if I multiplied it by z, I would come up with something with the same length, which means that this thing is acting as a rotation, it's power preserving. Okay, now I'm going to make it there be another one of these. And here's where I'm going to tell you about a choice I have to make, but the choice can happen later. Let's see. That's all right. Okay. So what I'm doing here is I'm correcting the individual amplitude of this oscillator to tend toward 1. And I'm going to do that same thing separately to the other one, although I could, if I wanted to, be doing something else, which is fixing it so that the sum between them have the total power that I want, rather than just a single one of them. I'm sorry, I'm still nervously tidying up because I know I'm going to run out of room soon. All right, that's all right. Time to quit being nervous and just take this thing and do my thing with it. Okay, maybe, I'm not sure. Take everything along. Actually, no, maybe not the inlet. I'm just going to, the inlet, I'm not actually using anything, but I might eventually want to throw something in here, and I want it to be thrown into both of these if I do. All right, so this one is now going to have a different, oh, what happened here? Oh, that's my wonderful snapshot device, which I should not have saved. Oh, come on. All right, what else? Yeah, good enough. We don't need that anymore. All right, and this one now we give a different frequency, say, and then I'm going to check and see if it's doing something reasonable out here. And by the way, I'm only listening to one of the two things, which is actually the imaginary part. Now, why are they the same frequency? Oh, thank you. It's the same delay. I need to give this. Oh, all right. It's a miracle I didn't just blow something up. Let's shut this thing up. And I don't know. All right. New name. Someone's following this, though, at least. Okay. All right. Let's see how we're doing now. All right. We got it. So I'm going to just leave both of these in the air. So these are now these two different frequencies. And I'm going to leave this kind of low so I can talk over it, if you can hear me okay. Yeah. All right. Now what we do is we start... Oh, I got to draw a picture next. Okay, so I'm going to shut this up. Oh, it's worse than that. I don't just want to draw a picture. I want to start talking about what it's like to couple oscillators together. And what you will get if you read the textbooks about coupled oscillators, and this was told to me when I was an undergrad, so this is basically culture that everyone should have. When you couple oscillators, it engenders a I should rather show you than the oscillators oscillate separately in a particular way. They each represent a mode, and then you can pretend that they're part of a single system that just has those two modes, but they are independent. They're not coupled. But then a linear way of coupling the modes is simply to essentially put a spring between the two oscillators. And then what happens is, when they're going in the same direction, they're happy because the spring doesn't do any work. But when they're going in the opposite direction, they get unhappy and they spin faster or vibrate faster. So you get detuning of one of the modes. Actually, both of them get detuned, but if they were, say, of the same frequency, one of them would go north and the other would stay the same. And in fact, what I'll do is I'll show you that particular special case quickly, and then I will move on to nonlinearity. So that requires some animation, which I'm not going to do live. I'm just going to go find where I did it. Where did I put it? That was bad. Let's cancel that and try again. Where did I put the thing? It's not there, so it should have been there. Drat. Oh, new. Duh. All right, good enough. Now what I'm going to do is go find, except I don't see it. Yeah, here we go. Sorry. And sorry, this is the sort of demonstration that you make in acoustics classes, except I've virtualized it. Someone like Dick Moore would actually show up with real springs and masses and show you how this works. But I'm going to not do that. I'm going to just so pretend because I'm a lousy animator that these are walls. They're fixed masses that never move, and these are two springs, and they are allowed to vibrate because they are in the air and they're attached to reality with a spring. And then there are going to be two different kinds of modes by which this combine. Oh, and here is a weak spring that's now going to couple them. So now you could pretend that spring is not there, and then each of these things has, say, the same resonant frequency, and one of them could be wiggling and the other could be wiggling. But physical intuition would tell you that once you put a spring there, it's not possible for one of them to wiggle and the other not to be wiggling. It will eventually transfer energy to it. So by what? So how do you think about that? Well, a way to think about that is this. So here are the two modes of the combined system. One is this mode, and sorry, this is stupid, but we're just going to be Mickey Mouse for a few minutes. So here's a mode. This is a mode in which both of the masses are moving in phase with each other. And now you can tell by looking at it that the spring that is coupling them is doing no work. Well, work is not the right word, but it's not doing anything. It's not applying any forces to these springs because its size doesn't, its distension, whatever you call it, extension, doesn't change by the fact that the masses are moving. But there is another situation, which is the two puppies are going out of phase like this. And that is a different situation because this spring is actually doing work. And what work is it doing? The answer is, you can think of it as, and this is a trope in physics. Whenever you see something that has a symmetry like this, you can pretend that actually you only see one half of this, and that there is another wall holding this midpoint of the spring fixed. Right? And you think of this is also the way you think about air columns. You think about, for instance, not to go into this, but basically this is the way you think. And so what you can really think about this is it's a mass that's connected to wall. It's connected to immovability by two different springs, one over here and one over here. And when you put two springs in parallel, you get another spring that just has a higher spring constant. You just get more springiness. And just to dispel one possible bit of confusion, it is not the case that this spring is doing the opposite thing from this spring because it's stuck to a wall on the other side. That would make it seem like that spring was opposing the other spring and therefore reducing its springiness. I don't know how to explain this, but it's just not the case. It makes it more springy. It doesn't make it less. Just use your physical intuition. For instance, if I put another very strong spring here like this one, it's not like it would cancel that one out. It just makes it more attached to non-movability instead of less attached. They add. And the way to say it really is, there's a potential function, and and where the spring is at rest is the minimum of the potential function, and the potential functions are both convex up because each of them separately would leave the mass at rest at the same place. And so when you add the two potential functions, they don't cancel out, they just get more, you just get a steeper parabola of potential, or a steeper potential well. All right. So what's happening then is that here's the mode where they are moving at the same frequency as if this didn't exist. Here's one where they're moving at a slightly higher frequency because this spring is adding to the spring constant. And then when you add two things that are slightly detuned, they beat, and they beat in an entertaining way. It's exactly like it should be, right? Which is to say, sometimes the two modes which are being superimposed are in phase on one of them and out of phase of the other, and sometimes they're in phase in the one and out of phase in the first one. And so it will do this forever until you give it some friction or something like that. So this is all just, this is cheating. I'm not actually doing a physical model here. I'm just computing the sinusoid that it should be the motion and doing this synthetically. But this is truth, right? And we can do this in our nice two oscillator model too. And do I have the courage to actually do it? I'm not sure, but yeah, let's not do it. No, let's do it, because it would be wonderful if it turned out that what I was telling you was completely false, and the only way to find out is if I do it and it turns out to give the wrong answer. So I'm going to caution you by saying that I'm now doing something that I've never done, so I'm not dead sure this is going to do what it should do theoretically, but who knows, it might. So I'm going to get rid of this. By the way, I'm going to remind myself what the other puppies... Oh, yeah, actually... Okay, so I've prepared a nonlinear coupling oscillator, good. But I'm going to actually make it rather than use the prepared one to show you what's going on. All right, so now, first off, try linear coupling here. So linear coupling means we give each one of these things a nice frequency. 220, I guess. It's a little... I'm not sure where we would be the most sensitive to, or where we'll hear it the best. So now we're listening to two things that are going at A. Now what I'm going to do is introduce linear coupling between these two so that you will hear an A and a slightly sharpened A, and the A will be in phase in the two speakers, and the slightly sharpened A will be 180 degrees out of phase. And if I do it just right, you'll actually hear the A beat back and forth between the two speakers, but acoustics being acoustics, I don't think we'll be able to hear that really happening, unless I do something silly like modulate it by noise, which then you will. But I don't think I feel like doing anything that silly right now. Okay, so how do you couple it? Okay, so first off, how do you even think about this thing as a spring system? And for that, I have to show you the picture again. I'm sorry, picture. How do you think about a spring system? You think about it. You can think about it this way. There are 2 degrees of freedom in mass and spring land. This is a single. Almost. This is a single... all right, let's get it really level. Yeah, pretty good. Okay, so this is a single mass on a spring, and now we're going to label the axes. This one is going to be displacement. We're going to be right, I'm not sure. Okay. Oh, you know what? I'm going to just call this position. And up here, I'm going to say this is velocity. And then, of course, so the position being 0 is the vertical axis. That's where you have only velocity and no position. And then the places at, and so here's this point here is the spring is at rest. It's not moving and it's not distended. Okay, now we distend it by, say, a unit, and then we let it go, and it starts accelerating, which means the velocity starts increasing, but it also starts moving inward. And pretty soon, all the energy is in the velocity. That's to say, it became kinetic energy. This is potential energy here, and that's kinetic. And so on. And so the spring basically, well, if there's friction, it will describe a spiral, but if there's none, it will describe a nice circle. Right? Okay, now, if you had 2 such springs, and of course I should have drawn this much smaller. Do I dare resize this? I might pay for this, but it worked. All right. All right, just had a very happy outcome of a very doubtful experiment. All right, so now there are two of these puppies rotating around, and now we need a way of describing what the force between the two things should be. Well, there's going to be some rest distance. Maybe the rest distance should be as it's described. In other words, this thing's at rest and that thing's at rest, and there's no force between them at that point. That seems good. And then as this spring gets closer to this one, or as this spring gets closer to that one. Oh, right. So if these two springs are at two different points, then the distance. So one of them's here. What did that do? Oh, I got to go back into this thing. Okay. So one spring is here and one spring is there. Then the distance between the two springs is just this horizontal distance. Not the vertical distance. So the vertical axis is velocity. We don't care about their relative speeds. That's not going to engender force. The thing that will engender force between the two masses is their distance, because that's the thing that makes the spring make force, is distance. All right? Okay? So all we got to do is if this distance is the rest distance, which is to say if this x value is the same as this x value, if it looked like this, say, there would be no force. But if this x is less than that x, there will be force pushing this one in that one's direction and this one in that one's direction, and vice versa. In other words, if the two x's are different from each other, then there will be a force to push them in the same in each other's direction. All right? So all we got to do is simulate the situation. Go over here. Now, so here's position. Well, actually, where should we look at it? Doesn't matter where we look at it. Sorry, I'm thinking about whether to do it after or before we've corrected this. Maybe the simplest way to think about this is to put the cool part, is to put the new part up at the top. But it's really academic. Which of these two we do? So I'm going to make some room in the usual way. Come here. That was bad. Okay, now I can move this down a little bit more. All right, this is going to be a lot less than you were probably fearing, right? So we're going to take these two things and subtract them. The two positions, right? So here's position. Oh, don't do that. So here's the position of spring number 1, there's the position of spring number 2, and if they are perfectly in sync and are tuned the same and have the same amplitude, this will be 0. Now we're going to take this thing and we are going to apply a force to this one, which is proportional to this extra distance, and we're going to, I'm not sure whether we should add or subtract, but we have to do the opposite to the other one, so it doesn't matter which is which. So we're going to add to this person's velocity, not to its position, but to its velocity, because force adds velocity to things. Because force makes things accelerate, and acceleration is change in velocity. So here's our velocity. So instead of just using the velocity, drat. Okay, at some point we're going to be doing an add, so let's do this now. There's an adder. Here's the same thing, but with the network to add something to the velocity before I start messing with it, right? And I'm going to have to do that same thing over here. So let's do it this way. It's not perfect. Let's do it this way. And now, what are we going to add? Well, okay, so first off, we have to decide some proportionality. In other words, there's going to be a spring constant which will tell us what the force is as a function of this distinction. So let's make a number box, and I don't know, but it's feeling like dividing by 1,000 or so is going to be a good set of units. Ooh, maybe, oh, let's be real gentle to start with. Can always get ungentle later. And then we're going to multiply that by this, just to make any factor times it. And then we're going to, say, subtract it from this one and add it to this one. That's it. That's the whole deal. Of course, since I've never done this before, we don't really believe this is going to work the first time or anything like that. So now, here's the oscillator. Here's the other oscillator. Since I don't hear anything, I can turn this off. Yeah, it's still there. So they're both doing the oscillator, and now I start giving it force. Yeah, I think we're safe. Go down, which is wrong. I have to give it a lot more than I gave it. Okay, keep going. At some point we're going to start hearing something, I know, because it can't just not do anything. Hello? What am I doing wrong? This should be... that should be screamingly different. Alright. Well, maybe what I'm telling you is just not true. What did I do wrong here? What you should have heard by, which you should already have heard very clearly was that, oh, no, it's all right. What's wrong with my patch? Oh boy. All right, well, I told you there was a good chance it wouldn't work. Do what? This one.
Oh, right, sorry.
Yeah. Well, I don't know. I'll go find out what's wrong with this and fix it. It could easily be that this stabilization is succeeding in stabilizing the frequency in a way that I don't understand. In fact, I could do this.
That little change at first.
Yeah, I sure heard that. Yeah.
I wasn't sure if that was like or not, though.
And it went in the wrong direction.
Yeah.
Okay, so let's fix it so that we can. Let's fix it so that we can turn the amplitude correction on and off. This is a little dangerous because, of course, when the amplitude correction goes out, well, you know what could happen. But let's just do it anyway. So now I'm going to listen to it again. Just one of them might do. And now turn the amplitude correction off. Oh, we just get a little bit of truncation error. Ooh, somebody else is doing something silly. And now I have to be able to give it an impulse to be able to make it sing. There's an impulse, but it doesn't do anything. Why not? Because, okay, impulse is going in and getting added to everything. 0 there. Oh, yeah, let's get rid of this now. Of course, right. Alright, so now we have two springs, but they're real springs now. And now I can start coupling them. And then it made him die. Nothing. Oh, listen to that. Got something. We just made it not function at all. What? Okay, now we let it fade. Yeah, I hear it. It's wrong. It's not what the theory said. Okay, and I don't know what to do about that. And then it just doesn't function at all past a certain point. And then we get that. All right, I don't know why this is happening. This is to be continued. What I'm going to do, rather than try to figure this one out, is to do the thing that I know works, which is to make a nonlinear coupling between the two springs. And there are bunches of ways of doing this. So what I'm going to do first off is just make them bounce off each other. And the way you make springs bounce off each other, and here I need a picture again, is you do this. When the springs get to where they hate each other, that's to say, when this distance gets too small, so that means that the masses are in contact like this, and they're moving like this, presumably, because they didn't get there by moving the other way, we don't think. Well, then suddenly the velocities just instantaneously get negated. So in other words, what you do is you set a threshold here, and when the difference becomes less than that threshold, then suddenly the two velocities, instead of being what they are, become negative what they are. This will never work. Well, somehow it does. I've seen it work. Okay, so, all right, so how do you do that? Well, you go over here. Of course, since my linear example doesn't work, what makes me think the nonlinear example will, I don't know. Okay, so let's take out this nonlinearity now. Let's put back the forcing. All right, now we should hear something. Why don't we hear anything? Interesting. That should be a hint. That should be telling me what I've done wrong.
Why should it tell you?
Well, I should be hearing music now because here. Oh yeah, you're right. But even when I don't have it at 0, it is not doing it. What is going on now? What did I change that suddenly made it turn? Oh yeah, right. Okay. These puppies are still doing their thing. All right, time to try the snapshot trick again. So what's coming out of any one of these things? Oops, no. Very small values. So that should mean that what's coming out of here is slightly bigger than 1, and it's slightly less than 1. So why does it conclude that it wants to attenuate it? Oh, duh. These numbers have to be negative. Otherwise, it's a positive feedback loop. All right, so now we can... Yeah, got it. Okay, so now we've got our oscillators back. And of course, this still doesn't work, does it? It works. Does the wrong thing. Oh, maybe it doesn't. Here's the deal. Well, I've got one problem, which is why don't we hear two pitches here? They are both coupled. All I've done is detuned them. All right, I don't know what's going on, but I refuse to worry about it right now. I'll worry about that one later. Okay, so this is now linear coupling between the two oscillators, which instead of making, and they're now, they are out of phase with each other, which is believable because they're phase locked. And now all I've done is I've managed to detune them, but they both get detuned the same way for I don't know what reason. Okay, now let's mute everything out. Oh man. Okay, all right, nonlinearity. So to do this, what we do is we subtract it again, and then we compare it to the value that below which we can't stand the thing going, whatever that is. And then if it does that, then we take the velocities and we force the velocities to be, in one case negative, in the other case positive. In other words, we replace the velocity by its own absolute value. And again, I believe if I do this wrong, it will not function, but I will just attempt to do it right. Okay, so to do that, we do this. We're going to subtract it, and then comparator. So now we're going to see, we're going to subtract a, what's the right word? We're going to subtract a threshold, which I'll say in hundredths. So, and then we're going to check whether the thing is positive or negative. So the way to do that is we subtract, we already subtracted it. So the way to check whether something is positive or negative is we multiply it by infinity, like this, and then we just clip it. So these two things make a comparator. Multiply by 10 to the 20th and then clip it between 0 and 1, because it'll never be between 0 and 1 after you multiply it by such a huge value. So it'll be 1 if the thing was positive and 0 if it was 0 or negative. Right? And if it's 0, we're just going to let this thing alone, but if it's 1, we will replace it by its absolute value. So to do that, let's see, I'm going to make this a plus. And we'll replace one of them by its positive absolute value and the other by its negative absolute value. Now, who is complaining? And why are they complaining? Oh, because I forgot the tilde here. Okay, so replace the thing by its absolute value. Well, it's easy to know how to get the absolute value. You just Deus object, get the absolute value. Thank you. Now, to take a thing and replace it by something else, what you do is you subtract the two, and that's what you would have to add to the thing. I'm sorry, you take absolute value minus the thing. Like this. That's what we condition. Ooh, sorry. This is the. Oh, come on. All right. There we go. So this now is the difference between the thing and its absolute value. Now, that is the thing which we can add to this, and it will replace the thing by its absolute value, because it's the difference between it and its absolute value. So, for instance, if I just added that to this, then that would be giving this thing its absolute value instead of it. That would be kind of interesting. Well, no, it wouldn't. That would be an oscillator that could never get a negative phase. It would just sort of get to 0 phase and then just keep butting against 0. That wouldn't do anything terribly interesting. But then what we do is we do that only in case we decide to do it, which is to say only in case this thing comes out 1. So we multiply this thing by this discriminating value, so that when the thing goes positive, whenever this number is positive, suddenly gets this thing replaced by its absolute value. And when it's not positive, nothing happens. And now we do the same thing to the other one, except that I believe in this case, at least my physical intuition, although my memory of this contradicts my memory of the patch that actually works. My understanding is that I now have to make this one be negative. In other words, one of the springs has to be moving away from the other, and the other spring has to be moving away from the first one. Right? So this is the thing we replace it by. So we now subtract the original from that, and then we do that only when this catastrophe occurs, and then we connect that like that. Did I do something wrong? I think I'm okay. But you can't even see whether it's okay or not, which is really bad style. So let's do something like this. Oh, I don't know who to move up. Where do I stop? All right, but now this can go down here. This can go down here. All right, and then we can sort of see what's going on, although not terribly well. Yuck! Well, I'm not going to... Oh, no, I didn't want to close either. Save that. Okay, now... now we have to say, what is this thing? And of course... Okay, so we're... what we know is that this... If these things are unit amplitude, this thing never exceeds 2. So if I set this thing to 2, or actually even more than 2, then this thing is always negative, and so this thing always decides to be not whacking. And then I'm going to change this threshold until they start whacking later. All right. So first off, do we hear our oscillators? And so that we can hear the oscillators better, I'm going to give them different pitches now from each other. All right. And now I'm going to start introducing the ouch and what's going to happen? Yeah, that's about it. So what happens is the springs start whacking each other, and then you get this, and that is just the sound of two things hitting each other.
Can you look at the waveform?
Oh yeah. Well, yeah, the waveform isn't going to be terribly interesting yet. I don't think. Oh, actually, yeah, it's not. We caught one. They're rare events right now. It's only going at 20 times. They're only hitting 20 times a second-ish. But I can fix that later. So what happened was it got to where they whacked, and then suddenly it just gave up and backed off, right? And now as I move them closer together, they do that more and more frequently. But it's slightly different points from each other. I think they're. Oh, I see that we're listening. No, I don't think so. That just changes the mix at which we hear them, I think. And then as we get it, so what I should say is that although they hit each other, they still basically cycle at this point. So you still hear the individual pitches, but that will quit being the case as we punish it more rigorously.
And the question, that's changing the overall period of that cycle, right?
Yeah, it just reduced the period of the cycle, and so you should, even at these levels, you should hear a slight sharpening. So here's the original pitches, and it's getting sharper. Both of them are. And then catastrophe. They just ended up getting synced. But now here's where it gets juicy. The point at which they hit, the point at which they get forced into sync. Changes depending on the relative pitches that you give them. So that was a nice major third, but should I put this on a, let's see, I'm going to put this on a metronome. Half a second. Good. Okay, and now as we change the pitches, different things happen.
So what's determining those jumps?
I have no idea. Well, it's good, whatever it is, but all right, so although I have no idea, I can at least sort of say this. The two springs are having, or the two systems are having to negotiate, are somehow negotiating a lower frequency that both of them can find harmonics of, that they can manage to vibrate at, even though it's not their favorite frequencies. And where that is, so it might have something to do with the least common multiple of the greatest common divisor of the two frequencies I give it, except that in general it will find something that's an approximate least common divisor. In other words, if they hit an approximate integer relationship, it'll find the submultiple that they're approximately at. But that submultiple jumps up and down in some way or other.
Does it also depend on how quickly we're changing? Like it might force it to jump into a different regime if you
that's a whole other thing. It is possible for the exact same numbers to give you two different results, and it can act stably at those two different values. And I don't know if I can just dial that behavior up, but I can try. There it is. So it changes at 192, but then it does this behavior all the way down to 179 or so. 180. There's probably a name for that. That might be bistable behavior, I'm not sure.
Hysteresis?
Well, hysteresis is a linear phenomenon, at least in classical electronics. It's a little bit that Brendan thing about the butterfly catastrophe, the idea that the path that you get to your place on the lower dimensional thing tells you where you are in the higher dimensional manifold. You know, mutter. And I don't know if I don't know how to say how you would use such a thing musically. You get it in real instruments too. You know, you get an instrument vibrating at a frequency, you can blow at it in a regime that should give you a different frequency out, but you would have to stop blowing and start again to get it to hit the other note, like splitting notes on a trumpet. And so I think this is essentially the same phenomenon, except in a more synthetic, simple kind of a situation.
Could this sort of thing be achieved without delay lines, just using oscillators and
Ooh, could you do this without delay lines? Well, no. The thing is, as long as you're doing it sampled, in other words, we're operating a sample rate. As long as you're making feedback stuff that uses sampled signals, then there's always a delay every time you feed something back.
Right.
And so, in some way, there's ineluctably a delay there.
Okay.
But, of course, the real world doesn't operate that way. And so if you were imitating a real physical system, let's see. Thing I should perhaps... Okay. By the way, I believe it's the case, although I'm not dead sure, that although I'm listening for some reason to the imaginary parts, I shouldn't be making any huge difference if I listen to the real parts. And the other thing is, it would be easier just to listen, just to have one volume control. So let's do this. And a thing to mention is that things feel or operate differently when these things are sort of neighboring, as opposed to at crazy intervals. So, for instance, here. So now we're 3 to 2-ish, but. Of course, one of the things that we could do is make them beat, and then we get things that just whack each other at the beating speed, right? No. What I just said is contradicted by what we're hearing. That should have just every once in a while whacked. Why did that not happen? Well, anyway. Forget that. Sometimes that's true. It was true when I got started because maybe that's because I had one of them very slow. I don't know. All right, well, maybe this is the thing about how the thing is bistable and you can sometimes get a behavior and then not be able to get it back. Different kind of thing happens when you set one frequency very low and another one very high, which is at some point it sounds like you're messing with timbre or with a formant or something like that. So now the bass frequency is sort of C sharpish, but this thing is now a kind of resonance on it. And I think another interesting, useful thing happened when you set a very low frequency. No, not yet anyway. Never mind. That's not useful today. Oh yeah, I can explain that behavior. Okay, so now what we have is motorboat, right? I don't know if the 18 hertz is mattering a whole lot, but now what's happening is we're looking at the faster of the two oscillators, the one that's going at 274 hertz. And now if, the thing is, if we actually tell the springs they're in the same place, like if this goes to 0, which is saying the two springs are actually at rest at the same place, they're basically always bouncing off each other. And then if we push them even harder at each other, at some point we get to where the spring just can't even make it all the way through its cycle anytime. And that raises the pitch of the whole deal. Just for the stupid reason that the cycle, we're using less of the cycles, so it takes less time. So at least in that regime, we can explain why the pitch is going up. And the rest of it, I don't know. I mean, they're just sort of, there are little bits of behavior that you can come up with some kind of vague explanation for, and the rest of it is just kind of doing stuff, and you just have to go find your way through it. By the way, this is screaming for some kind of physical interface to play with, because obviously twiddling with number boxes is not going to give you the feel for this thing as a potential musical instrument. You'd really want to have, you know, a nice plastic ball that you could squeeze in various ways to get it to do its thing. All right. And that would be a hardware project someone could try. Okay. Okay, now that was all by way of just sort of giving you the sound a little bit more so you could ask questions if you have thought of any about why it does what it's doing or anything. Yeah?
I have a question. So when you subtract the first two delay lines,
Mm-hmm.
I mean, so you keep saying that you're subtracting the position, right? But, so that's the same as like the amplitude?
I might not have said that terribly clearly. So in each of these cases, this is one of the systems and this is the other.
Mm-hmm.
And this is position and velocity.
Yeah.
Okay, so this is subtracting the two positions, which is simply saying how far they are apart as a positive or negative number, depending on where they're crossed. But then you said, is it amplitude? And then the answer is yes, but in the sense that all these things are amplitudes.
I guess my question was, are they in phase, like their position, or why isn't it always 0? I guess.
Why isn't it always 0?
Yeah.
Well, if I uncouple them, then this is the difference between those two signals, which is the difference between two sinusoids,
Mm-hmm.
which is therefore, it ranges all the way from +2 to -2.
Okay. But if they were in phase with each other, wouldn't it always be 0?
If they were in phase with each other, then it would be 0. If they were tuned the same, and if they were in phase with each other.
Yeah.
So if I said 274 there and 274 here, I think, okay, so I don't know what phase they're in now, but just smashing them together will force them to go into phase. And then they'll just be happily in phase until I do something that they can't deal with anymore. Oh, why did that happen? Like I got all the way from 200 down to 0, and then it won't give me my 200 sound back. Go figure. Can't get it back anymore. All right, never mind. Don't know what's going on. Okay, yeah. Again, just hardware project. Yeah?
Where are those like really sudden jumps in timbre coming from? Because you're changing sort of a continuous, well not really, but roughly continuous parameter, and suddenly the timbre just snaps to something else.
Yeah, it's. I think that's the fact that both of them are vibrating at frequencies different from their own resonant frequencies, so that when that tension gets too great, then it jumps to another solution to find another compatible resonant frequency that they can stand to be at together.
So those jumps are sort of determined by previous states of the parameter. You could just instantaneously initialize the parameters to those states and have the same timbre.
Might be able to. I mean, it seems like sometimes you can get back to things and sometimes you can't.
Because that's really interesting, the fact that like it's very determined on like previous energy states.
Yeah, right. Yeah, like where you are depends not just on what the current parameters are, but the path by which you got to the current parameters. That's right. And yeah, I don't know what else to say about that. Oh, except I should go back and just try to, let's see, where are we? Oh yeah, so I should just go back to the picture. Actually, I'm wondering, when it does change regimes audibly, I'm wondering if this picture actually shows you anything about what the change is. Oh dear. Ooh, okay, so there it's got it doubled its period by doing something, but now I could probably get back to 264 a different way, and now it's not doing that. So yeah, I don't know. Okay, let's turn this off. Okay, so yeah, but just to go back to trying to be a little bit more clear about what the relationship is between these delay lines and all the rest of it. The simplest way to describe it might not even try to say that. Supposing, the simplest behavior you could get is if the coupling never happens. In other words, I give it a threshold that it never exceeds so that the two are uncoupled. And at that point, each of these things is operating independently because the only pathway that gets between them is this pathway and that pathway. Right? So that's where the coupling is. When the coupling is not in action, then what's happening is this is a point in the plane, and here's a new point in the plane, and basically what's happening is the new point is just the twist of the old point. And the twist operation is this operation of multiplication, which just twists the thing. So if it does nothing but twist, then it makes it. Oh, and we're only listening to the x-axis because we're listening to the real part. So you just get a sinusoid out. So that's the relationship between this picture and that. This z, that is the sine and cosine of this frequency, which is being computed inside the twist object here. This is cosine and sine. And this is complex multiplying the cosine and sine of this thing by this state, which is a complex number. And that's happening in lockstep every sample. Right. Yeah?
Pardon me if I just wasn't here for any focus, but what is the noise source for?
Oh, it's worth reminding you of because I didn't say this for a few weeks. The noise source is just there because if you just did this without the noise source, it would just be at 0. 0 is an unstable point, but it is a point which has the property, it's like a ball on the top of a hill. Mm-hmm. So what you do is you add a little bit of noise to the ball so that it starts rolling. Anyway is okay, and then finally it finds the proper limit cycle that's actually stable. So it's really just there to keep it from being 0, especially when you close the patch and reopen it. And then suddenly it's not doing anything because everything was 0, and that actually mathematically is okay, even though physically it's not, because it's unstable. Okay. Yeah. All right. Now, what I have to do now is save this in its current state. Let's just be a little bit more friendly here. We're not using this impulse, by the way, and we're not using that. Let's not even have that. Oh, you know what? We may want this later. Well, it's easy to make it. To hell with it. Okay, good enough. Twist. We're not using twist anymore. Good. 3 more resonant. Okay, good. Now I'm going to do a save as, and now start talking about better behaved ways of coupling oscillators. Well, of course, good behavior makes for bad music, but it might actually make for slightly easier understanding to just sort of give you more continuous, smooth kinds of things. So the situation physically, so I'm just going to say coupling in general. I don't know, coupling. More coupling. Right? Okay, so So the physical situation here is what's the right word? Impolite to the springs, to say the least, because physically what's happening is when you replace their instantaneous velocity by its negative, is you're giving the thing an infinite acceleration. So everybody aboard the spaceship gets creamed, right? So it's, or to put it another way, that creates a discontinuous derivative in the output signal, which looks like one of those spikes that you saw in the graph, and that means plenty of high frequency content, although, you know, it's going off, when you get a discontinuous derivative like that, like a point, that's really only 1 over n squared roll-off of harmonics, which is manageable. It's not like, you know, it's not like a flat frequency response going out, but you still could be getting fold over, and anyway, it's going to tend to give you maybe a little bit buzzy sounds, and maybe you like the buzz, but maybe you'd like to be able to choose whether you have the buzz or not, right? So what would be a thing that, a way to think about these two oscillators, which would be coupling them, which would be continuous but not linear, right? So we tried the linear thing and it actually failed to do the correct thing, so let's not try that anymore. But now let's just talk about continuous nonlinear ways of coupling these things. Well, a possible answer of many is this. So here's the coupling. Let's take the coupling out, except I like the idea of having a control which psychologically is going to be how much we're coupling the things. So let's leave that there. But what I'm going to do is I'm going to make the coupling take the following form. I'm going to take one of the oscillators and I'm going to take the other of the oscillators and I'm just going to twist them like this. Going to do it, yeah, I don't know. I think for the sake of simplicity or the sake of something, I'm going to do it to real parts. Let's get rid of this. Let's get rid of this. We're not doing that anymore. All right. Now, so what's going to now happen is I'm going to take the two real parts and I'm going to do something to them. I don't know what yet. And then I'm going to use the outputs the way I was using them before. Where was that going? No, drat. I think that was going right here. It was just getting added to the noise, yeah. That's bad style. All right. Now, this, since we're giving it the zeros to twist by, this does nothing so far. This is just multiplying by 1, if you like. It's nothing. Now, so what are we going to get the twist value from? Well, the answer, okay, I already lost that control. Okay, so I'll just get a control. So at some point we're going to want to take some value, any value at all, right? And then we're going to multiply it by some coefficient. And throw it in there. That's all. Almost all. There's another slight thing that I should probably... Sorry, I'm thinking too hard. There's a thing that I want to change now about how the amplitude of the thing is controlled. And the thing is this, right now I have both of these springs set up so that they both like to have amplitude 1. It's going to turn out to be potentially more interesting, or at least potentially more realistic, to allow the springs to have different amplitudes, but just to ask for the total power of the system to be 1, not just the power of each spring individually. So what we can do is we can add an additional degree of freedom to the system by saying we're not going to force the springs individually to have, an energy of 1, which is to say the x squared plus y squared, or the velocity squared plus the position squared, or whatever it is, right? That energy, it doesn't. In general, we could allow energy to actually pass from one of the springs to the other, and the thing that should be energetically conserved then is the total energy of the whole mess. So what I'm going to do that is actually get rid of unit polar because it's no longer suitable for doing this. And instead, did I just do, oh man. And what, the other problem that I'm having now is that it seems to me now that it would have been a lot cleaner to do this before I do the twisting, but sorry, it's just going to be what it is. Okay. So now what I'm going to do is, now, rather than use unit polar, I'm just going to do this by hand. I'm going to square this value. Oh, yeah, go away. Square this value. See now, I'm suffering because I'm trying to get the total energy of the system after we've done the twisting thing, and maybe, but the twisting thing doesn't even change the energy, so why do we even care? Why don't I just do this? Let's make this clean and neat. So we're going to just do it up here. Total energy, total energy, total energy, total energy. Then we're going to add all four of these things up and take the square root of that. Square root or the inverse? Square root, yeah. Oh, well, actually, were we? Yeah, that'll be. I'm not even sure we need to take the square root, but I'll do it anyway, just because it'll remind you that that's what we're doing. And then after that, that now is going to be the thing that we use to compute the coefficient by that we're going to fix this by. So we'll take this and move it up here. And as a function of the square root, sorry, don't need unit polar. Not sure whether we need, oh, don't want that. Right, and then as a function of this square root, we check it against 1. We figure out by how much we want to correct the thing by, and that becomes the thing that we multiply everybody by. And everybody is real, imaginary, real, imaginary. Okay, so this is just what you've seen before. No, I don't need that anymore because that's going to be there. Sorry, I'm trying hard to make this thing be nice and clean and easy to understand. Yeah, that clip was part of the deal. Yuck. Now, if I was smart, I would put this in a sub-patch. But I'm just going to resolutely refuse to do it the smart way for some good reason. Alright, so now we're going to do the same thing to... Okay, let's move this down. Don't need this clip anymore. Don't need these puppies. Things got simpler. Still need the noise, but we're just going to add it there. Alright, starting to be reasonable again, right? Oh, in fact, we could actually use the same noise. That's just salting us. Okay, and now let's see, that's going to go there. This is going to go there. That's going to go there. Now we need another thing like it down here. Oh, times. Is there any chance I actually got this right? And if I got it wrong, it might blow up, so let's be careful listening to this. There. All right. Now, just to review everything that's gone on here. What's happening now is read our 4 delay lines now, which is the state of 2 springs, if you like. Get the total instantaneous power of everybody by taking the sum of everybody's square, reduce it to amplitude by taking the square root, so it's the root power now. Then we're give that a number. Then we are checking it against 1, making a correction factor, adding that to the normal value, which should be 1, clipping it to make it reasonable, and then multiplying everybody by that before we go on to the rest of it. The rest of it then is the following. What we were doing before is we were just twisting these two and then twisting these two associated with each of them with its own frequency. But now what we're going to do is we're going to mess with the position of the two and make those two positions interchange in some way. Actually, yeah, it should have been, if we were talking about a nonlinear coupling, it should have been the velocity that we did that to. But I'm just not going to try to be that correct, because in fact things are symmetric at this point to the point that it doesn't matter which we do. Okay, and by the way, this is being multiplied by 0, so this is not going to do anything right now until I do something. Okay, so this should just be the two oscillators making two sinusoids again. I hear one of them. I hear that one. And this one is doing nothing. Oh, right. But of course I only fixed it so that the total amplitude... Yeah, I don't know what's going on. This is not good yet. Okay, so why is it dying out? It's happy. And so this believes that the total power here is actually 1, which maybe it is. But now I'm irritated because one of these oscillators is not speaking and the other is. So I could just feed them both an impulse, and that should make the other one sing too, right? Yeah, there it is. Now every time I give it an impulse, different amount of energy will go into the two into the two oscillators. The total power should be constant, but you hear the balance of the two changing, right? Okay, so that's consistent with what I've just done. Now, to make these two be coupled, first off, to make these two be coupled in a linear way, let's just make this be a signal and start twisting. Now, why did one of those disappear? Well, it's just what it is. No, I'm sorry, signal. So it seems like the energy just naturally seems to flow to one side as opposed to the other, and that's just unavoidable, so that's just what we'll live with. So now if I start twisting them, you get kind of what you might expect. Well, I don't know if that's what you expect or not. But in a word, what happened here is this. There are enough degrees of... Okay. This is not nonlinear. This is now introducing a linear coupling between the two, because in fact twisting this by a fixed number that doesn't depend on the data, that's a linear operation. So it's still a linear, well, it's a linear coupling of two springs, and so all I do when I linearly couple them is I detune the two springs. So we are back in the situation where we just added a rubber band between the two springs, except that didn't work, and this is now working a little bit better than that did. But other than that, nothing interesting is happening. Okay, so now what else can we say about this? Oh yeah, and it still seems to like for the energy to slop over onto one side, but don't know what to say about that. Now what we do is what we can do is we can say, I'm tired of this. Let's just go back to the original situation, but instead add a multiple of one of these states. Doesn't matter what. Well, anyway, it doesn't seem to matter what. And nothing happens. Oh, something happened. I wasn't expecting precisely that kind of behavior. Okay. Why did it happen like that? Yeah, same thing there. Well, I guess I might not have been quite right when I told you it didn't matter what I hooked this thing up to. Well, no worries. Let's just hook it. Oh, were there two connections there?
No, it's to the
what did
light bulb.
What did I just break?
Oh, we just
Oh, that's not good. Okay. Well, let's just try one of the imaginary ones instead. I think it works better when you don't. Yeah, right. It works better for I don't know what reason when you use the. Sorry, let me go back and say something about this. In a physical situation where there was coupling between two mass and spring systems, it should be the positions of the two springs that impart new velocity on the new springs. So what we had done before was we had measured the two, and now I'm sorry, I've now, without thinking, I've sort of switched position and velocity in this discussion, because now what I'm doing is I'm making a measurement which is about velocity and having it change the positions. And I really should have made the twist be among the velocities and the positions, but maybe I'll fix that. Let's fix it. All right. Let's just be clear, which is to say make this thing operate in a logical, correct, honest fashion. So we'll take the velocities and twist them among themselves. And the positions will just be the positions. Nobody's going to move discontinuously. Right, and now the other thing is the amount by which we mess with the velocities is going to depend not on velocity now, but on position. So if I haven't lost my mind, this should now sound basically the way it did before. Well, yeah, sort of, anyway. Qualitatively similar. Okay, so there's the linear sound, and here's what happens when you mess with it. All right, now, okay, so what's happening is, instead of just taking the velocities and replacing them with their negatives, or replacing them with their absolute values, forcing them to be positive or negative, right? We did another thing which was energy conserving, which is we just gave one of them some of the velocity of the first, but did that reciprocally. In other words, we mixed the two velocities. This doesn't actually have any physical reality to it. There's no situation that I know of where you actually mix two people's velocities, like add. Actually, isn't that an exchange of momentum?
Yeah, there's different mass.
Like you give one of the masses a little bit of the first one's velocity and give the first one a bit of the other's velocity. But the problem is, if you just there's something wrong with that, because no, there isn't. Never mind. Maybe that's a reasonable way to think about it. So going back to the picture here. So we have two masses on springs, which are two systems that normally would move around in circles. And what we were doing before was so the velocity is vertical. So a thing that we were doing was we were forcing one of the springs to be moving in the positive direction, the other spring to be moving in the negative direction, by basically taking the thing wherever it was, and if it was on the top half of the circle, bashing it down to the bottom half of the circle. Notice that that's energy conserving, in the sense that whatever your distance is from the origin, when you just bash it to the negative half plane, it's still at the same distance as it was. So that bouncing operation was an energy preserving thing, which is nice because it means we can have nice stable network again. Another energy preserving thing might be to give to mix the two velocities in an energy conserving way. And the energy conserving way to mix the two velocities is this. It's just and this is strange, taking the velocities and graphing the two velocities on a different plane from the planes that we're looking at. Here are 2 planes. These are position versus velocity. It's also possible to think about another plane. There are many other planes that you could try to show this on, but one of them would be velocity 1 versus velocity 2. Just take the vertical axis of one and the vertical axis of the other and call that a plane. And of course the 2 have different amplitudes in general, so the thing isn't even moving in a circle in general. And it's an ellipse, and the ellipse points in some weird way, who knows. But still, it should be possible to take the current position of our velocity hood and just rotate it to some other place. And that preserves the total kinetic energy, which is the sum of the squares of the 2 velocities, which is the square of the distance from the origin. So you can do that. It doesn't, I still can't convince myself that makes any physical sense. It is imparting one of the things with some of the other velocity and vice versa, but really, it's not, who knows, right? But at any rate, it's energy preserving, and furthermore, it's not. It's nice and highly continuous in the sense that it's a continuous function of this angle that we're asking the thing to turn by. And what is that angle? Well, that angle is one of these 2 puppies' positions, or both. Add them or subtract them or whatever. Just make any linear combination you care about these 2 velocities, and figure that that's positions, not velocities. Where they are is going to control what the force is between them. And then take that and pretend that its action is going to be just to take the 2 velocities and switch them around. And that's a nice continuous thing that you could do. Oh, it's continuous, but it's strange. It's not linear because these are linear position, but then this thing is a rotation. It's not a linear. It's not a linear thing. It's not a linear function of this position because that rotation is a matrix, which is the sine and cosine of this position. So it's taking sines and cosines of things instead of linear functions. That means we're back in frequency modulation land in some way of thinking. And so here we're just taking those 2 velocities and coupling them together and then making those be the 2 new velocities. And then all I can say about that is the results are entertaining. Of course, the higher the gain you throw something, the higher frequencies you're likely to get out of it. And this will just keep doing things like this no matter how much I punish them. And furthermore, it really depends on what 2 frequencies I've got going too. So now we've got nice bass clarinet multiphonics. Didn't even have to buy a bass clarinet. Sounds just like it. It's 1 hertz. I gotta give one of them a little bit of frequency. Oops, found a regime where it doesn't do much. And so on. Oh yeah, and we're getting nice graphs too, look. Yeah, now what that means, I have no idea. That's a better picture than I've gotten so far tonight anyway. Yeah, so if one of you can understand why that behavior is what it is, then you can probably write a PhD thesis about it. But it's exactly what it should. It looks the way it sounds. Now that was 2 oscillators. Obviously, you should be doing this with like 50 oscillators.
Can we save this?
Oh yeah, let's save this. But actually, to be a little bit more, what's the right word? A little bit more pedestrian about it. What's the sum total of all the junk we could do here? It's something like this. We could take all possible pairs of these things and twist them and make those things be any linear combination of these 4. There are 6 possible combinations. There's 6 possible choices of 2 of these 4. And there are 4 things that could affect any of those 6. There are 24 possible parameters that you could throw at this thing if you wanted to do it fully in general. Although I can tell you that by the time you got past about 2 or 3 parameters, you're in deep enough in parameter space that everything sort of just sounds the same. So I wouldn't advise you to give yourself more than 3 dimensions of control on it. And of course, these frequencies are salient no matter what. Those are things that have a clear sort of effect. A thing that you might want to consider doing is if you're twisting real to real like this, twist real to real and imaginary to imaginary by the same angle. And then at least you're sort of obeying the complex structure of the 2 things. But I don't know physically whether that means anything or not. I could tell you something mathematically about it, but I don't know whether that actually would have any thing to tell you or not. This is nothing like the simplest physical model that you could put on coupling oscillators. A simple physical model might be something like this. Simple physical model might be, why don't you take 2 springs and hook them up to the same mass. That's coupling for you. And then put infinite mass there and infinite mass there. Sometimes people use ground to talk about infinite mass, right? And now make there be 2 different spring constants, and then you know the thing will operate at one frequency according to this spring constant and another frequency according to that spring constant. And furthermore, your physical intuition should tell you that if you start one of them going, it'll start the other one going too. So that this is in fact a coupled system. A way of thinking about this is there's a potential well. You can talk about the potential energy that's present just due to the displacement of this from its rest place. And that potential well looks something like this. Horizontal, please. So what I'm going to do is I'm going to try to draw a horizontal plane in perspective. So think of that as a horizontal plane, and then the vertical axis is going to be up on the page. Except I want to get this over a little bit. And then, okay, so this is this dimension is how much the spring went this way, and this dimension is how much the spring went this way. And of course, there's a spring constant which makes it like to be at the middle. So this is a potential well on this dimension, and furthermore there's a potential well on the other dimension, which has a different slope because it is a different spring constant. And then if you want to couple it, you just add to that any other surface you want. Well, that's not quite right, because you should add any other surface you want that has the property that it be zero at the middle, that it have no derivatives at the middle. In other words, there's no force there. Has no second derivative at the middle because the second derivative is just the first order spring constant. So actually this should be cubic function, which is tangent all the way up to the second derivative at the origin. Oops, didn't draw that one perspective very well. That would look like, can't do it. I don't know how to draw. Oh, okay, just stop there. So think of a cubic curve with no constant, no x, and no x squared terms, but x cubed terms or higher. Add all that junk that you want to the potential function, which then will introduce some kind of force to this system. That would be however this thing deviated from just being a perfect spring this way and a perfect spring that way. And that would be a good mathematical description of everything that you could talk about coupling. Of course, that's 2 modes of vibration now. So get a nice trombone or something that has maybe 50 modes of vibration that are in the audible frequency range if you play at a reasonable fundamental. So then you have 50 oscillators, which means 50 dimensions of this thing. And that means this cubic polynomial has how many coefficients? About 50 cubed, which is thousands. So you're not going to really, you're not really going to be able to measure those thousands of coefficients by getting a real trombone and trying to find out things about it. You would have to actually design your thing somehow. So why don't you just do something completely artificial like this instead? And just have fun doing computer music and forget about the trombones. Let them just be what they are. I don't know. Or, to put it another way, or to make another suggestion, if you can think of some way of organizing one of these things that would have a desirable behavior, where desirable could be anything that you think is desirable, because desirable is a subjective term, then figure out how to make the network do it and go to town. The only thing is, I don't know how to tell you what sorts of networks would behave how, except just to build a bunch of them and try them and see what you get. And then hopefully at some point, if you pursue that for long enough, you'll start to get an intuition for why they act the way they do, and then be able to actually design things for them. Yeah. Okay, so anyway, this could have been 24 times as much junk as it is, and then it could be more oscillators. Or you could take it in some other direction, which is what's coming next, which is seeing what happens when, instead of just having each sample affect the next sample, start adding longer delay lines in, which would be more evocative of situations where, for instance, you might be in a real room or have a column of mercury or some cool thing like that to play with. But that is another subject which I'm going to sort of not get into today because it's a big topic in and of itself. Questions about this? Yeah.
So if you had multiple oscillators, right, if you were trying to couple multiple modes in this way,
yeah,
you would have to come up with a rotation, like a twist operator that preserved it was energy conserving for all the oscillators that it would twist, right?
Yeah, and there's something I probably should have said that I didn't, which is that you can apply this twist to any two things, any two of the positions or velocities, or a position or velocity anywhere, and then you can do that as many times as you want. Mm-hmm. So the way you really do it is you probably do these things in series. Mm-hmm. In fact, that's like another way to think about it, or another way to maybe get ideas is, you look at this puppy. Here's a reverberator. I don't want help. I just want to look at it. But why did I not get? Oh, it's Rev 3. Sorry. There we go. Here's a nice thing which I'm not going to try to explain completely, but it's just a bunch of delay reads and a bunch of delay writes and a bunch of mixtures. Where are the mixtures? The mixtures are in 4 stages. Here, we're mixing 2 adjacent ones. Here we're mixing 1 and 3, 2 and 4, 5 and 7, so on like that. This is a butterfly network. And in being a butterfly network with 4 stages, it actually manages to mix everybody with everybody. So there are sort of logarithmically complicated ways to do a huge amount of mixing. But on the other hand, it's kind of a special case. It would not be the case that any real object no real object would ever mix itself in such a parsimonious way. It would do something much more horrible than this. And if I were going to try to make an arbitrary power-preserving matrix of 16 values into 16 values, there's something like 16 choose 2, 15 by 150 different coefficients to specify. something like that. Yeah, so that's a thing. So that's a direct analog of, that's the reverberator, but that's a direct analog of this stuff, where you just take two things and mix them, as long as you do it in a way that preserves power, and then you can do that as many times in whatever orders you want. And those are all linear operations on these signals, but they are nonlinear as a function of how much angle you ask to twist the thing by. And the thing I don't know how to tell you about is this. I don't know, well, I sort of know why I just corrected the power of the whole system instead of trying to correct the power of subsets of the system. It's well, obviously, it's so that energy can actually pass from one mode to another, which is sort of a physically believable thing that could happen. But on the other hand, it seems like that could be a thing that you would also want to play with in a more detailed way too. In particular, when you take out this twisting, all the energy seems to tend to settle into one of the oscillators at the expense of the other one. Well, maybe you do want to do something that keeps the energy more distributed among the oscillators than that. I don't know. What I've done so far has always been based. As soon as I start doing this stuff, I've always gone ahead and just corrected the total energy of the system. And anyway, why is this a linear function of this thing? Why am I just making the angle be that? I could use the absolute value, or I could use something else, right? Right now I've got such a good setting, I don't want to mess with it, but try squaring it, or try taking the absolute value, or try thresholding it, and then you might get things that crash into each other only at certain amplitudes. That all works too. Oh, in fact, thresholding is worth checking out. So let's do. All right. So, with apologies, let's just assume we can find our way back here if we need to, although probably can't. Here's our. Okay, just made it linear. Good. Now what I'm going to do is I'm going to just take this thing and threshold it by multiplying it by infinity, and then clipping. -1 to 1, I don't know, whatever. Do I dare connect this? Yeah, because everything's power preserving, right? We're safe. Here we are. So we're back a little bit to two springs bouncing off each other. What P? Oh, Stockhausen. That's Contacta. Not really. Now I need the Nachnal, and then I can get the next page of Contacta. Okay. Anyway, okay. Why this thing just did that, I have no idea. All right. Oh, yeah, that's a nice setting. All right, but that was just a thing, right? How many functions are there? Lots, and they all do things, right? Of course, the simpler ones are probably more interesting than the complex. But that was clipping, which is this kind of thing. There's absolute value. There's linear, which is what I showed you first, and just just whatever. Oh, should I put it back? I should make it be. Okay, that was a thing, but then the other thing was just doing this. That's how we had it before. Let's just check. Yeah. Well, we don't have quite the same setting, but anyway, the setting will be lost when I close the patch. All right. Questions?
You put these up right after class?
It depends on, well, yeah.
Yeah, exactly.
I might be able to. Yeah, I have to plug my machine in. And,
That's fine.
Yeah, the thing is, if I don't do it, I'm going to forget. Yeah, so why don't I just do it? All right, so I'm going to take my network cable out to remind me that I'm doing that. Other questions? It's the analog of the finger around the string around the finger. No questions? Okay. All right.
I was just going to
Yes, it's an update. All right. Next week is delay line. More than one sample of delay and what that does to us. And then after that, there was something else I told you at the outset. Now I've forgotten already. But there's another thing. What? Oh, continuous time. Right. The Moog filter and the Lorentz attractor, which require that you do things in continuous time instead of discrete.